Hi everyone, it's Professor West again, and we're going to go over 1.2, Applications with Linear and Rational Equations. So 1.2 is just applications of 1.1. What does that mean? It's just word problems of 1.1. So we're just going to do some word problems here. The most important part about word problems is to, first of all, take a deep breath. You got this. Second of all, you're just going to want to either draw a picture or in some way organize the information. And third of all, at the very end, you're going to want to write a sentence. Okay? So, our first example is, how much 4% saline solution does a chemist need to mix into her 200 milliliters of 12% saline solution to make a 9% saline solution? And by the way, guys, this is on that worksheet I passed out, so you can pull out that worksheet. Feel free to pause the video, pull out that worksheet, and fill it in. If you lost the worksheet, no issue. You can just write along with the problems. But what we're going to want to do for this problem is we're going to want to draw a picture of what's happening. So the chemist, I'm just going to draw a picture of the solution that she currently has. So she currently has a solution. She has one. She has actually 200 milliliters of it. 200 milliliters, and it is a 12% saline solution. So what does that mean? That means her solution is made up of 12% saline, and the rest is probably water. So currently, the chemist has a 12% saline solution. Now, what is she going to do next? Well, she is going to pour in 4% saline solution. So I like to think of that as adding, I'm pouring in here, I'm pouring in 4% saline solution. 4% saline solution. We don't know how much saline solution she's pouring in, so I'm going to call that X. Okay? X is the amount of saline solution she's pouring in, and it's going to be, again, in milliliters. So maybe you want to write milliliters to help you remember. So currently we have 200 milliliters of 12% saline solution, and we're going to pour in 4% saline solution of an unknown amount. So we don't know how much saline solution we're pouring in. However, we want to figure out how much that is. That's what the question is asking us, right? It says how much 4% do we need? So we're going to, again, call that X because that's what we're solving for. Now, what do we want? Well, in the end, we want 9% saline solution. So I'm going to draw an equal sign to kind of show that's what we want. So I'm going to draw a little cup here for 9% saline solution because that's what we want. And how much 9% will I end up with? Well, we started with 200 milliliters, and I'm just going to pour in X amount. So if I'm just pouring in X amount, that should be 200 plus X. 200 plus X milliliters. So do you see here? I have 200 milliliters of 12% saline solution, and I'm adding X milliliters of 4% saline solution. And so since I have 200 already and I'm adding X, I'm going to end up with 200 plus X. And our goal is 9% saline solution. So now that we have all of these, for each of these, we're going to multiply down. So for each of these, I'm just going to multiply down. Multiply down. Okay? So as I multiply down, that's going to kind of tell us of the amount that we have, how much of it is made of saline, right? I have 12% solution, 12% saline solution. I have 200 milliliters of it. So if I take 12% times 200, that'll tell us how much of this solution is saline. And we can use that to figure out what X is. So that's what we're going to do. So when I multiply down, I get 12% times 200, and I'm just going to drop off the milliliters here just to keep it all as numbers. So I have 12% times 200 plus 4% times x equals 9% times 200 plus x. 200 plus x. Okay? So all I did was just multiply down from my picture, right? So making a picture is very important for these problems. It can kind of help you process the information. So then, after I do that, I'm going to turn my percent into decimals. So if I have 12%, that as a decimal is 0.12. So now I have 0.12 times 200 plus 4% is 0.04 times x equals, and 9% is 0.09 as a decimal times 200 plus x. All right, so now this should look just like those linear problems that we were doing earlier. And we have decimals here. So this is where I would pull out the calculator and start calculating. So on my calculator, 0.12 times 200 is 24. So this here is 24. So I have 24 plus, I can't reduce the 0.04x, so plus 0.04x equals, and here I need to distribute. So 0.09 times 200 is 18. So I'm going to write 18 here after putting that in my calculator. So 0.09 times 200 is 18, and I use the calculator for that. And then 0.09 times x is just 0.09x. So plus 0.09x. All right. So now we're going to want to get all of our x's to one side and all of our non-x's to the other side. So I think I'm going to subtract both sides by 0.04x just so we can avoid negative numbers. So on the left-hand side, I'm going to get 24 plus 0.04x minus 0.04x equals 18 plus 0.09x, and on this right-hand side, we're also going to subtract 0.04x, because whatever you do to the left-hand side, you have to do to the right-hand side. And on this left-hand side here, the 0.04x and the negative 0.04x cancel, leaving us with just 24. So 24 equals, now on the right-hand side, we have 18 plus 0.09x minus 0.04x. You could put 0.09 minus 0.04 into your calculator, and what you would get is 0.05. So 18 plus 0.05x. Now we want to get all of our non-x's on one side, so I want to get rid of this pesky 18 here. So to do that, I'm just going to subtract 18 from both sides. So I have 24 minus 18. Let me move that over. 24 minus 18 equals 18 plus 0.05x minus 18. Because whatever I do to the left, I have to do to the right and vice versa. So now 24 minus 18 is 6. So I'm going to write 6 here. And again, you can use your calculator for this. And on the right-hand side, I'm left with 0.05x. 0.05x. Okay? Now, to get rid of that 0.05x, I'm going to multiply both sides by 1 over 0.05. So on this left-hand side here, let me get that ready here. I'm going to multiply by 1 over 0.05 times 6 equals, again, whatever you do to the left, you have to do to the right. 1 over 0.05 times 0.05x. Okay. So on that right-hand side, you're just left with x. And when you take 6 and you multiply it by 1 over 0.05, you end up with 120. 120. So now we are left with 120 equals x. So if we look up here, we were asked how much 4% saline solution does the chemist need to mix into her 200 milliliters of 12% saline solution to make 9% saline solution. So imagine I go up to this chemist and I just say 120. She's going to look at you very confused because she's going to think, what do you mean 120 what, right? It took us a little bit of time to figure out the problem. She's already on to something else. You just come up to her and say 120. She's going to get a little confused. So it's important that we write a sentence. So let's write a sentence. So I'm going to write my sentence, which is going to say, to make a 9% saline solution, the chemist needs to add 120 milliliters of 4% saline solution to her 200 milliliters of 12% saline solution. So this tells us exactly what we want right here. The chemist needs to add 120 milliliters of 4%, which is what we found right here, to her 200 milliliter solution of 12% saline to get that 9% saline solution. And we just wrote exactly what we need right here. So you want to write a sentence that tells us exactly what you found and gives the chemist enough to work with. So that is the answer to this problem. So next, if you flip to the page, to the back page, we're going to have another problem, which you can see peeking through here. But at the very top, I left some space because we're going to write a quick equation down, the distance equation. The distance equation. So the distance equation is D equals RT, where D is distance, R is the rate or speed, and T is time. Okay, so that is the distance equation. And we're going to use that in the next problem. So let me keep that up while we look at the next problem here. Oliver participated in a 41-mile biathlon that included running and bicycling. He spent 1.75 hours on the bike and 0.75 hours running. If his average speed on the bike was 12 miles per hour faster than his average speed running, then what is his average speed running and his average speed cycling? So we want to find his average speed running and his average speed cycling. So we're first going to say, hey, let R be Oliver's running speed, because that's what we're looking for. So let R be Oliver's running speed. Okay. And then we also want his biking speed as well. So let's say let B be Oliver's bicycling speed. Okay, so we have a variable now for both of the things we want, right? We want his speed running, which we called R. Now, let me get a different color here. I'll go with yellow. Want his speed running, which we will call R. And we want his speed cycling, which we called B. Okay? So, another thing to note is here we see that his average speed on the bike was 12 miles per hour faster than his average speed running. Okay? His average speed on the bike was 12 miles per hour faster than his average speed running. So that means that Oliver is 12 miles per hour faster on his bicycle than he is running. So that means that his biking speed equals his running speed plus 12. His biking speed is, equals means is, his biking speed is his running speed plus 12 miles per hour because he is 12 miles per hour faster biking than running, right? So B equals R plus 12 because if we take his running speed and add 12 miles per hour, that will be his biking speed, okay? So now we want to organize the information into a chart, okay? That will really help us with figuring out the answer. So let's make a little chart here, okay? Let's see, something like this probably. You know, like that. And your guys' doesn't have to be perfect. Mine's not going to be perfect. Okay. So I'm just going to kind of just make some lines here. Something like, maybe like this. Oh, made that a little off. Okay. Again, it doesn't have to be perfect. I even think I made this a little lopsided. You know, that's okay. And we're going to want to put our distance here. And then our rate and our time. And on the left-hand side, he's going to either be running or he's going to be on his bike. So biking maybe we'll put here. Okay? So, because we know that d, distance, equals rate times time, we kind of have here that d equals, see if I can get this here, d equals our rate times our time. Okay? So, let's kind of get a strategy here. So we know that our running rate is r, because that's what we said right here. We said let r be Oliver's running speed. So I'm going to put r right here. Okay? And now we already know the time. We already know the time for his running from up here. We know that he spent, and let me get rid of all these other underlines so you can see what I'm about to highlight here. We know that he spent 0.75 hours running. Okay? So his time running then is 0.75. And because distance is rate times time, his running distance is going to be 0.75 times r. So that is his running distance. Because distance is rate, and his rate was r, his rate was r times his time, and his time was 0.75. All right. Now for biking, you might be tempted to put a b here, but we don't really want to put the b here because as we said earlier, b equals 12 plus r, or r plus 12. So b equals r plus 12. So actually we want the r plus 12 because having one variable is very helpful to us. So we're going to say b equals r plus 12. And let me rewrite that. R plus 12. Okay, and that's what's going to be important. So I'm going to underline that. B equals r plus 12. That's what we're going to actually use. Okay? And then we already know the time he spent biking from our problem. He spent 1.75 hours on the bike. So that means that our time here is going to be 1.75. Okay? And again, distance equals rate times time. So what does that mean? We're going to multiply our rate and our time to get our distance. So again, we don't want to use b, we want to use r plus 12. So over here, we're going to get 1.75 times 1.75 times r plus 12. Okay? So now let's think about it now that we've organized our information here. The total distance, right? The total distance of the biathlon, well, that's going to equal our distance ran, so the distance we spent running, distance ran, plus our distance biked, right? The total biathlon is running and biking. So the total distance that the biathlon was is going to be however far we ran plus however far we biked. So if we look up here, I'm going to erase these underlines so you can see what I'm going to highlight next. Oliver participated in a 41-mile biathlon. What that means is that the biathlon was in total 41 miles. So if I come down here, I'm going to replace total distance with 41. I'm going to replace total distance with 41. Okay? Because that was the distance of the biathlon. Now that's going to equal the distance that we ran, but we found that already. We found that right here. That's the distance spent running. So that means that the distance ran is 0.75 r. Okay? Now plus the distance biked. So the distance biked is going to be this here, 1.75 times r plus 12. So this is going to be 1.75 times r plus 12. Now, look here, aren't you glad that we did not use this b here, right? If we use this b here and put that here, we couldn't solve for anything. But since they are both r, both of these are r, that means we can solve for r, and we can use that to solve for b later. So let's solve for r. So I'm going to take 1.75 times r. So I have 41 equals 0.75 r plus 1.75 r, and then plus 1.75 times 12. Now this is where you pull out your calculator, right? So 1.75 times 12 is 21, so plus 21. All right, now it's time to combine like terms. So I'm going to get 41 equals 0.75r plus 1.75r. Now again, you can use your calculator here, and when you do, you're going to get 2.5r. 2.5r plus 21. We want to get r by itself, so I'm going to subtract 21 from both sides, right? I want to get rid of that 21. So I'm going to go 41 minus 21 equals 2.5r plus 21 minus 21. Okay, so 41 minus 21 is just 20. And on the right-hand side, we're just left with 2.5r. Now, to get rid of 2.5r, we're going to multiply both sides by 1 over 2.5. I'm going to multiply both sides by 1 over 2.5. One over 2.5 times 20 equals 1 over 2.5 times 2.5r. Now, if you did 20 times 1 over 2.5 in your calculator, you would get 8. So I'm going to get 8 equals, and on the right-hand side, that reduces to r. So I get 8 equals r. Okay. Now, we don't just want r, right? Because what is r? R is the running speed, but we also want the biking speed. So remember, b is our biking speed, but we have a way that relates b and r. So I'm going to use this equation to get b. Okay? So we know that b equals r plus 12. But we know r. R is 8. R is 8. So that's going to be 8 plus 12. And we got that from here. This here is how we got the 8. Okay? So that's 8 plus 12. And 8 plus 12 is 20. Okay? 8 plus 12 is 20. So now I have both my running speed and my cycling speed. But I'm not done quite yet because I need to write a sentence, right? If I just show up and say 8 and 20, they're going to get a little confused. So we want to answer the question. So let's go back and see what the question said. The question was, if his average speed on the bike was 12 miles per hour faster than his average speed running, then what is his average speed running and his average speed cycling? So they want to know, what is his average speed running? What is his average speed on the bike? So let's write a sentence that answers that. So I'm going to say that Oliver's average speed running was 8 miles per hour, because that's what we got for R. And his average speed cycling, or on his bicycle, whatever you want to write, as long as it gets your point across. His average speed cycling, we found here, was 20 miles per hour. And then that's all you need to answer the question. Oliver's average speed running was 8 miles per hour, and his average speed cycling was 20 miles per hour. So again, with these, it's just the stuff that we were doing in the last section, except you just have to be able to set it up. So here are 2 examples of some possible word problems that you might get to set up. Okay? If you have any questions, feel free to email me. And I hope you guys stay warm, and I'll see you later.